So here we are going to see how an exponential growth of wind energy has happened in India. Okay, um, until 2016, 2017, it was growing very nicely. After that, it dropped because of the solar coming inside, and wind was not able to meet these policy changes in the government. Okay, uh, earlier what they did, as I told you in the beginning, they invested in wind farms to write off their profit in the first year itself. Suppose I get 1,000 crores profit in a textile mill. Okay, if I invest 100 crores of 1,000 crore in a wind farm, that 100 crores I don't need to pay tax. Is it clear?
Yeah, understood.
Yeah. In addition, there will be a 10-year tax holiday for whatever you generate using wind turbine, and the income from wind energy is having it was having a 10 years tax holiday
Exemption.
exemption. So these things was driving earlier. Okay, and then later on it was also feed-in tariff. Feed-in tariff means if you pump in 1 unit, this will be your charges. That is feed-in tariff. Assured income. That was driving the wind farm development till 2017. Then they brought in the bid-in tariff, competitive bidding inside, just like solar, reverse bidding.
Hmm.
Because of that, wind fell down drastically, wind installations. And again, in the last 3 years, it started picking up. Okay, wind. Uh, so, in essence, against 100 gigawatt, 60 gigawatt of wind, achievement at 22 is 40. Now it's about 50 gigawatt now. Okay, in 24. In now April 24, it is about almost close to 50 gigawatt, which you can ascertain from your MNRE website. Okay. Yeah, this is again just to show you the how the wind changes. Now, how wind energy is converted. Uh, if you feel that you are confident in certain areas, let me go faster.
Okay, okay.
Okay. Okay.
All this are I do not know.
Okay. Wind energy conversion is kinetic energy in the wind. Kinetic. What is kinetic energy? Uh, half mv square, mass
Hmm.
into v square. V is the
Square.
wind velocity. That is the
Hmm.
kinetic energy in the wind. Okay.
Hmm.
And in 1 second, uh, if so much of wind mass is moving, that mass moment of inertia, mass into inertia will give you the total for thrust on the wind turbine. Okay, so we try to get the kinetic energy in the wind through a rotating element, that is a wind blade prime mover. This is called a prime mover. Okay, rotor and the hub is called a prime mover. Okay, using a rotating element, you try to capture the energy. That means what you are doing mechanically, you are rotating a blade with a which is fixed to a axis. Okay,
Access. Hmm.
that means you are getting into mechanical energy.
Hmm.
You are converting kinetic energy of wind to mechanical energy. Is it
Hmm.
clear? Okay.
Yes.
Under mechanical energy, the rotor can have maximum efficiency of 45 to 52%. I will tell you why. Okay. Okay. Rotor can have maximum efficiency of 45 to 52% efficiency. Then mechanical energy has to be uh, using a gearbox or without a directly coupled generator is possible. The gearbox can have an efficiency of 95 to 97%. Why do you need a gearbox? Can you tell me? We are, we are,
For
we are using
rotating.
the we are using the wind to rotate the wind rotor. Okay. Why do you need a gearbox?
For the rotating mechanism, sir.
Yeah, the rotor will rotate in a very small RPM, revolutions per minute. Say 10 to 20 revolutions per minute maximum. And the modern very large wind turbines will even go 5 to 15 revolutions per minute. That's all. Okay. If it is 10 revolutions per minute, uh, 10 by 60 will be the frequency. Okay. 1 by 6. About 0.12 is the frequency. 0.12 hertz cycles per second. Is it clear?
Yes.
10 revolutions per minute means RPM.
Mm.
That has only cycles. How many cycles per second? 0.12. 10 by
Point one.
60, 1 by 6. So it's about 0.12 cycles per second only. Is it clear?
Yes.
It is very slow. So when you come to the generator, if you convert 50 cycles per second per minute, if you want to convert, what is the requirement? 15 to 60 is 3000.
Yeah.
3000 revolutions per minute is required at the generator end.
Mm.
Is it clear?
Yes.
So to convert 20 RPM or 10 RPM to 3000 RPM, you need a gearbox. Is it clear?
Understood, sir.
Yeah.
Now only understood.
And of course, this 3000 requirement of 3000 RPM can be reduced by properly
Mm.
designing the generator with multi-pole. Okay. If
Okay.
you generate,
So in
if the
simple
generator has multiple
definition,
pole, two
gearbox
poles
means.
means, yeah, you are an electrical engineer, you know it. If the generator has two poles, the required RPM will be 1500.
Uh,
If it has four poles, it will required RPM will become 750. Like that.
mm.
With multiple poles, required RPM level can be reduced.
Reduced.
Okay. So like this, you need a mechanical energy to electrical energy. You need a conversion system. Agreed. Okay.
Yeah.
That conversion system sometimes gearless means what will happen is they will back to back rotor and generator will be back to back.
Mm.
Okay. In
Mm.
that case, what they do is, okay, they will manage the pumping into the grid by using power electronics. You
Sir, one
get the
minute.
point?
If a gearbox definition means it convert. What is the definition we say for gearbox, sir?
Yeah. The gearbox will have two sides of the gearbox. Okay.
Mm.
Okay. One side it will be a low speed shaft. Okay. The other
Okay.
side will be a high speed shaft which will be interfacing to the generator.
Generator.
So the low speed of the rotor will be converted to high speed, the requirement of the generator. That is the purpose of the gearbox. Is it clear?
Yes, sir.
Okay. That is, you are stepping up. Just
Stepping
like
up.
a step up transformer, you have
Transformer.
electrical.
Ah.
Similarly, stepping up mechanical energy, you need a gearbox.
Okay.
Okay, you got it?
Got it, sir.
Okay. And then you have this generator. It needs to give 220 volts, 50 hertz constant, isn't it?
Yes,
To
sir.
interface with the grid.
Mm.
So, but the wind is continuously varying. Okay. So the wind power will be alternating current with variable frequency. Okay.
Same frequency, no, sir.
No, the frequency will keep on varying. The as the wind fluctuates, as the rotor speed changes,
Ah.
there can be constant rotor as well as variable speed rotor.
We're talking
Modern wind
frequency
turbines are
with
all
respect to
variable
mechanical
speed rotors.
energy.
Yeah,
Frequency with respect to mechanical energy.
yeah, it will
Ah.
be varying. Okay.
I said frequency with respect to the electrical.
Yeah,
Electrical
electrical.
system.
Yeah, electrical at the grid end it will be constant. Okay, at the grid end it must be constant. But
Yeah.
what is received as a mechanical energy may be having variable amplitude and variable frequency.
Ah.
So what you have to do is take the AC current generated by the wind energy, okay,
The
con-
variable amplitude.
yeah,
It's
variable amplitude, okay,
mm,
and variable frequency will come. You take that and go through the power electronics box, AC, DC convert, and from DC, like our UPS inverter, you convert it back to constant frequency, constant amplitude, current. Is it clear?
yes, sir.
So the magic is done by the power electronics in the case of wind turbines with
Um,
variable speed operation. Okay, then only you can get more energy captured from the wind. Okay,
okay.
uh, we will go further. You will know clearly, more clearly.
Okay. Okay.
Okay, okay.
Okay. Mm.
This
So
rotor, yeah,
this will be in the this power electronics. This will be in
in
the
the
gear
yeah, it will be interfacing along with the. It will be interfacing both the gearbox control, the
and the
rotor blade control. Everything will be there.
okay.
Everything will come in the power electronics. There will be sensors from the rotor blade. There will be sensor from the nozzle anemometer, wind velocity. Okay. There will be sensor input from the gear. Okay. The low speed RPM of the low speed shaft, high speed shaft here. All the inputs will be going into the power electronics. And then
Mm,
it will convert AC to DC and from
okay.
DC to AC in the required frequency and record constant amplitude 220 volts, 50 hertz for interfacing to the grid. That magic is done by the power electronics. Okay,
Yes, sir.
right. Let me go to the other point. So, how do you get power in the wind? What is the power in the wind? We said kinetic energy is half mv square. M is a mass, okay, mass of the wind that is flowing through the rotor, and v square is the incoming free stream velocity, wind velocity
Mm,
in meter per second, and A is the swept area of the rotor, the circle diameter. It is pi r square or pi d square by 4. Okay, A here is a swept area of the rotor. Do you get it?
yeah.
And uh, half rho A v cube. V is the instant wind velocity. V cube is the power in the wind. Just remember, this is only power in the wind. It does not show the efficiency. Okay, right. Now let's go to the 1 minute. I think I am missing one of the important slides. Okay, I think I'll go in this. Okay, uh, concentrate on this. Okay, huh? This picture.
Yeah.
So
Mm,
if we have the incident wind speed at V, okay, and this is the wind turbine, the plane of the rotation of the wind turbine. Okay, is it clear?
okay. Yes,
So
sir.
the wind is approaching the wind turbine normally, perpendicular to the plane of rotation. Okay, and this is enabled by a mechanism called yawing. By sensing the direction of the wind, the yawing mechanism will turn the wind turbine blade and the rotor to the wind direction automatically. Okay,
Yeah.
so that's called yawing mechanism. So
Spelling, sir.
YAWING. I'll be discussing yawing in future in the subsequent slides. Don't worry.
Okay.
Okay, I'll transfer the slides also to you. Okay, right. By yawing, the rotor will align itself normal to the wind direction. Okay, automatically, and this wind velocity after it is passing through this the wind rotor, can it be zero behind the wind turbine? Can it be zero?
Yes. Zero.
It
Begin
cannot.
the turbine, it will be.
it can never become zero because it will get reduced. Okay,
Reduce.
velocity will get reduced, but it will not be zero because it's
Zero.
in an
Okay.
open atmosphere.
Ah.
Okay, if it is
Okay.
zero, what would have happened? 100% of the kinetic energy would have been captured by the wind rotor,
Okay.
which is not possible at all theoretically.
Okay. Hmm. Okay.
So that limits the efficiency of wind energy conversion to kinetic energy conversion to mechanical energy by the rotor.
Hmm.
Okay, there is a limitation.
Okay.
Okay, let me uh, just change to uh, another PowerPoint where you will find it more clear. Lingam, I think. Are you seeing this wind energy perspectives and prospects?
Yes, sir.
Okay. I'm just going to, yeah, the wind energy early applications are, yachting, grain, grain
Hmm.
winnowing. It is called winnowing, grain cleaning, and water pumping, and rice mills in Holland. All those things were early applications. 1 minute, let me. Yeah. This is how it rotates. The wind turbine, how it works. The wind comes, it rotates. There is a low speed shaft here. After the gearbox, there is a generator high speed shaft. Okay, and as the generator runs, it gets the output. But here, the wind turbine works like this. I think. Let me. I am just missing my known slide. Okay, I'm just looking for a slide which I have not put in to
Okay.
explain to you. Uh, I'll have it in this. Yeah. Are you seeing wind through a steam tube?
Yes, sir.
This is from a book, actually. It's a very old book. Joshua Ernest, Torrey Visualis. 2015 it was released. Okay. So, as I told you, the wind velocity is coming here. Okay. This is a rotor. And if you have to maintain mass, moment of inertia, and momentum, then you will get two equations. Okay. The power before and power. Okay. This is power before and power after, and this is power captured. Okay, so this is the equation. In the downstream side, the V2 will be, as I told you, it will be lower, isn't it?
Yes, sir.
Because I told you the V2 cannot be zero because there will be air coming from here, air coming from here. Okay, so it will never become zero. So there will be some relative velocity left. Okay, and that the difference in velocity will be half mv square. And next slide, if you go, so that will be captured by a tip velocity. There will be a limit of the efficiency, the power coefficient. So this is 59% is the theoretical limit in an open atmosphere. Okay, in an open atmosphere, a rotor can capture only theoretically only 59% of the energy in the wind. Okay, It is depending on the blade tip speed ratio.
Mm.
Okay. Tip speed ratio is nothing but if n is the revolution, rotor speed in revolutions per minute, RPM. Okay. If n is the RPM, n by 60 is cycles per second. Agreed?
Yes, sir.
Into 2 pi will be give you omega. Okay. Cycles per 2 pi f is equal to omega. You remember? 2 pi f. F is
Okay.
frequency. So cycles
Mm.
per second is nothing but frequency. N by 60 is frequency. Okay.
Mm.
2 pi 2 pi into frequency f is called omega, angular velocity. Okay.
Mm.
Angular velocity of the rotor into the radius of the blade will give you what is the tip speed, how the tip speed will move. Is it clear?
Yes, sir.
Okay. So based on the tip speed and the incident wind speed, you can define this equation. This equation. This is called TSR, tip speed ratio. That divided
Mm.
by the mean wind speed, incident wind speed V.
Mm.
That tip speed ratio divided by the mean wind speed V bar is called tip speed ratio. That and the power coefficient, there is a relation. How much power can be extracted by any rotor,
Mm.
however aerodynamically designed it is. However
Mm.
aerodynamically designed it is, how
Design.
much power can be extracted? Theoretically, only 59%.
Mm.
Okay, that is why the practical achieved results are somewhere around 45,
To
so
50%.
40 to 50% maximum. Maximum. Is that clear?
Yes, sir.
Okay. Uh, that the funnel like thing you see here behind the wind turbine, obviously, if the mass flow in this circular area is V1 into area here, okay, and that circle has become, after going through the rotor, venture tube, okay, rotor, this circle will become bigger, okay.
Mm.
V2A2 must be equal to V1A1, otherwise there will be in between some vacuum, isn't it? There
Yes,
should be
sir.
continuity of mass as well as continuity of momentum.
Mm.
Mass into velocity is momentum.
Mm.
Momentum should be also continuous. Mass also should be continuous. Am I correct?
Yes, sir.
So small A1 V1 must be equal to A2 V2. That is
Mm.
why, because this area is big, this V2 will be small. So that much energy must be left out of the that will definitely be not captured by the rotor. So maximum efficiency is only possible
What?
59% theoretically. Maximum achieved is 42 to 50%. Okay.
Okay.
But gearbox efficiency can be designed by design, but with lubricants and all that, you can go to 95 to 97%. With power electronics, you can have generator electricity can be also 95%, even more
Mm.
modern days. Okay, right. Now let's go. What are the other controls we are building in to optimize the wind? Uh, before this, I think before this, shall we see quickly aerodynamics of wind? Okay,
Mm. Mm.
I'll just cover aerodynamics of wind. KCG will give that. Okay, so this is a recent uh, presentation made in KCG College of Technology. Okay, in one of the faculty development programs. So hope you understand what is a aerofoil.
Yes.
Okay,
And
aerofoil
what
has
is the fan now?
is not like a fan. Aerofoil is a blade cross section, the cross section
Mm.
of the blade.
Okay.
Okay,
Mm.
cross section of the blade, and the shape is what matters. It makes it aerofoil. Okay, aerofoil has got a leading edge, which is a rounded edge, and a trailing edge, which is a sharp edge. Okay, uh, okay. Now, and this horizontal distance is chord. Don't have to capture all this in your mind. Don't worry. Okay,
Okay.
aerofoil is one in which if you allow wind to pass through, it will not separate from the surface anywhere. Okay, it will smoothly go through that like a fish. Okay, aerofoil. Can you imagine like a fish how it is swimming into the water without any splash? Similarly, the aerofoil section will allow air to pass through without separating from the surface. Okay, right, like this smoothly. There is no separation. Okay, and by this, I think you would have seen on the wing side of the aircraft
Mm.
during takeoff, it will completely be closed.
Yeah.
Okay, and they will raise the engine so fast and get the best of the lift. Okay, you have to optimize lift. Again, I'm missing one more slide. Let me. Okay, I'll go to this. Yeah. This is aerofoil shape is like this. Okay, when the aerofoil is facing a wind. Okay, or when the aerofoil is moving in the air, like the aircraft wing. Okay, both ways are okay. You imagine both ways. Okay, either the wind turbine blade is facing the wind. Okay, or the aircraft wing is moving in air. Is it clear?
Yes, sir.
So you develop you develop one force perpendicular to the aerofoil, that is called lift. One force in the line of the wind direction, that's called drag. It is a loss. Okay, so you have to maximize more lift and less drag. Then only you will be able to get the torque. Okay,
Mm.
and whenever you shift the aerofoil, uh, when you are taking off, the aerofoil in the aeroplane automatically will be looking upwards, right, from this horizontal
Yes.
position.
Yeah.
So
Yes.
that means it is developing more lift to take the payload by really burning the gasoline fuel and taking a very high speed, 800 kilometer per hour on the runway.
Mm.
So it develops an enormous lift to take the tons of the payload which it is carrying, 300 people or something.
Mm.
Okay. Similar way, the wind turbine blade has to optimize the gentle breeze from the gentle breeze by turning the aerofoil slightly left or right. Okay. It should optimize the lift and reduce the drag to minimum. Then only you will get maximum wind power. Why? I'll tell you. Uh, are you able to see my camera?
Yes, sir.
Okay. If this is, let us say, one of the blades, okay, or let me 1 minute. Let me bring a wind turbine. It's easier to understand from a wind turbine. Are you able to see the wind turbine?
Yes, sir. Yes, sir.
Okay. If the wind is uh, coming like this, okay,
Mm.
and this is called the leading edge. Okay, this
Mm.
one, this tip, this is called trailing edge, which is sharp. That is, the cross section is shown here.
Okay.
Cross section is shown here. So
Yes, sir.
when it is generating, if the wind is coming like this, it generates uh, a drag load which is in the direction of the wind, okay, and a lift load perpendicular to the direction of the wind. If the wind is coming like this, lift load will be perpendicular to the direction of the wind. Do you agree with me?
Yes, sir.
Okay. When there is perpendicular to the direction of wind, it is coming here like this. Okay. Load is coming like this. That
Mm.
means this load into the radius will be the moment at the shaft. Torque, this lever arm, into the load which is captured at the tip will be it will make the wind turbine rotate. So you have
In
to,
between your line got broken. So in between your line got broken.
uh, is it okay now?
Ah, now okay. Yes, sir.
Uh,
You said no lift
yeah.
when the
Uh,
wind is.
yeah, when you optimize the lift which is in the direction perpendicular to the direction of the wind. If the wind direction is
Mm.
like this, lift is
Mm.
perpendicular to the direction of the wind. That means if there is a load applied here, the blade will rotate.
Okay.
Okay. If a load is applied in the direction of wind, the blade will bend. Okay. Is it clear?
Yes, sir.
Okay. So you have to optimize the lift so that you are able to get maximum torque. The lift into the radius will give you the torque. The
Okay.
torque means torsion in the shaft. That means it will rotate. From
Okay.
all the blades from every point. If the load is in this direction at this point, okay, in this direction, that will all in this direction perpendicular to the wind, then it will also rotate. The load here also will rotate maximum. So now
Mm.
you can imagine a load at the tip will give more torque than a load at this point. Is it
Mm.
clear? Because
Yes.
the distance is small.
Mm.
Okay. So most of the wind energy is captured by 1/3 of the wind turbine blade effectively.
Um,
Okay. Most of the, because that is having the maximum uh, lever arm.
right.
Okay. The purpose of engineering design is to optimize the lift and reduce the drag. If the drag becomes more, that is when in the case of cyclone, okay, the 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 wind turbine will not be allowed to rotate. The pressure in the air is so much in the direction of the wind, so the lift will not be generated, drag will be generated more like this. It will try to stop the wind rotor. That is why we automatically stop the wind rotor and avoid damage.
Okay.
Okay, so
Okay, sir. Understood.
that is a basic approach to engineering design.
Line
Okay,
design.
yeah, and don't worry about all these theoretical equations. All these are codified
Okay.
into very nicely uh, codified into softwares which you can use. Okay, so based on the tip speed ratio, you can define a power coefficient. Okay, so with the so by pitching the blade in its own axis, by pitching the blade in its own axis, you can change the lift depending on the wind direction and wind velocity.
Mm.
Is it clear? That's
Yes, sir.
called blade pitching
Line pitch.
in its own axis. That is one of the controls, which is
Okay.
which if it is efficient, the wind turbine will produce more power.
Okay.
The modern wind turbines will sense the wind in the front. Okay, how much fluctuation is coming to your blade, it will sense by laser anemometers. They use a laser anemometer here, okay,
Mm.
and capture the wind in the front 100 meters away, okay, and analyze the wind and be ready with the right kind of pitching they should adapt to the blade,
Okay.
so that it will maximize the lift and get excellent pitch control and more power.
Okay.
Okay, this is one of the
Okay.
controls. Okay, and next control will be by blade efficiency can be improved by uh, full pitch control, the entire blade being rotated like this, okay, or partial pitch control and boundary layer control. These are all modern techniques, okay. By keeping some holes here to avoid this friction induced by the thrust. This turbulence over the wind turbine blade will introduce a heat and thrust. Lot of energy loss will be there. To avoid that, I think you would have seen the while you are landing, okay, to reduce the friction, the aircraft in the aircraft wing, there will be part of the plates opening.
Yeah.
So similar to that, now modern wind turbines will have bleeding holes to avoid excessive friction, boundary layer control. Okay, all these are by improving the efficiency of the blade in pitching, you can get more power.
Okay.
And there are several lift boosters. Okay, lift coefficient can be increased. Several methods are there to boost the lift of aerodynamically designed blades. And I think, do you want in detail in all this?
No, sir. I think
Okay,
this is
yeah,
too.
you just have an
Yeah.
idea. There are
Yeah.
a lot of methods now. Memory
Yeah. Yeah.
alloys, memory alloys, semiconductor alloys are there, which can also
Okay.
allow a very intelligent way of shifting. And you would
Okay.
have seen in some aircraft they have a bend at the this thing.
Mm.
The aircraft thing, you will see a bend, right?
Yeah.
It
Yeah.
is
Yes, sir.
it is called a winglet to reduce the tip losses. Okay,
Ah.
okay, it's called winglet. So
Mm.
similar things are possible. A lot of innovative efforts are being pumped in now. Okay,
Okay.
uh,
Mm.
the wind tunnel cannot be used for all these studies because uh, this is not the way. Okay, right.
Okay.
Okay, then we will go back to yawing. Okay, well, if you have time, we will come back to that. Okay, once again.
Yeah. Yes, sir.
Uh, yeah. I think you want to break at 1:30, yeah,
Yes, sir.
and rejoin
When
at
can you join, sir?
to 2:15 or 2:30.
Yes, sir. Yeah, 2:15. Okay, sir. 15 or
Good.
2:30? What? As per your wish, sir.
No,
2:30, sir.
yeah, 2:30 is also okay. Fine for me.
Okay.
Okay, right.
Okay.
This after finishing this one level, 1 minute,
Yeah. Yes.
we'll close it after yawing. So one is pitching. Okay, another is
Mm.
to keep the full area circle. Okay, the wind turbine should face the wind. Okay, otherwise, if it is inclined wind, it will see the wind will see an ellipse, which whose area will be less.
Mm.
Okay, for that reason, there will be a yaw motor and yaw system in wind turbines,
Mm.
which will allow the depending on the direction of the wind, it will allow the wind turbine to rotate to any
Okay.
direction like this. Okay, it will turn to the wind direction.
Mm.
Okay, so that it faces the wind normally, so that maximum production swept area will be available, because swept area is in the formula power.
Mm.
Okay, that is why we'll try to keep the yaw error should be minimum during wind turbine testing. It should quickly, when the wind direction changes, it should quickly go to the direction.
Mm.
So how quickly it goes is called yaw error. This will be found during wind turbine testing prototype. So
Mm.
yaw error is also will be recorded in your SCADA.
Okay.
Okay, because yaw error should be minimum so that wind
Mm.
turbine is more efficient. Okay, I think we'll start with the controller in the afternoon.
Yes, sir.
We'll start at this point.
Mm.
Okay, right.
Okay.
2:30 will assemble. Okay.
Okay, sir.
You want
Same
to
to
keep it open or you want to send another invite? I'll keep it open. I put off my
yeah.
camera and
Yes,
audio.
sir. I do. Yes, sir.
Okay, okay, right.
Thank you.